So it seems we're recording, and we'll continue the story from where we left off. We were dealing with something called linear transformations. After a weekend like this, you might have forgotten what that meant. So let's start with a simple example that clarifies what a linear transformation is. So the title is Line of Transformations. And it is also called mappings. Now we'll take your example so you can hear what it means. Imagine you have a space. Where is the vector? I'll just draw a circle. You should imagine this is a space where vectors exist. So there could be a vector here. Then we have a mapping or a transformation. Sometimes we also call it a function, which can send us from that space
over another room. So here is a
good
room.
with the overall. And here there were also some vectors. You could choose the path that was like that. This space here, it's where you pick vectors from. It's where you send them to.
And that's it. I'm off.
This space here is usually called V. And that space over there is usually called W. And these are just names. So you don't need to worry about
It
them.
was so far up. It was just something she used to call it.
And what happens from here to over there is described by a transformation. You can think of it as a function. So that function f that you see there takes vectors from inside V.
There is a bag full of vectors V.
And then a vector. It could be called x vector. If it is 2 or 3 dimensional, we've decided to place the vector arrow on top. If it has more than 3 dimensions, we just put a line underneath. And when f has acted on x, a new vector y comes out. So you should think of this space as the input space, because in that space, all the vectors used as input resides. So this is our input room. And the space over here is where all our vectors land after being sent by f. So that's our output. And now we can give an example to show how this could work in practice. So here comes example 1. Imagine you have a function f, or a transformation as you might also call it, or a mapping as it can also be called, that takes us from
what is referred to as R2 ends in R2. What does that mean?
When one writes a capital R, it should be thought of as the real numbers. When there's a 2 above, it means the real numbers and the real numbers in the plane. So this is the 2-dimensional vector. Imagine that the space I'm selecting from has 2 dimensions, and the space I'm landing in also has 2 dimensions. This means that the vectors here have an extra new coordinate, and the vectors over there also have an extra new coordinate. However, that's not always the case. This is just a very simple example I'm making now. It could easily be that one goes from 2 dimensions to 7 and 3 dimensions.
20 dimensions.
So I'm going to try another example that's a bit more complicated, but we'll start with a very simple one, where I go from 2 dimensions to 2 dimensions. And now I need to invent what f does, meaning this transformation, what it does to those vectors, to turn them into those vectors over there. So I'm just imagining something, but I make sure to come up with it in a particularly simple way, which means it can be called a linear transformation. When something is particularly simple in mathematics, it's often linear. So what I imagine this function f does to my input vector x is the following.
Should we pay?
It takes 2 times the first coordinate of vector x. So this vector x has a first coordinate called x1. And to that, it adds 3 times the second coordinate to vector 1. And that's just something I'm making up right now. There's nothing special about the number 2 or the number 3. I'm just coming up with it. But there is a very good reason that it does not say 2 times x1 squared plus 3 times x2 to the 5th, because if it did, it would not be a linear transformation. Because when the only thing that happens to the coordinates of the input vector is that they are multiplied by constants and added together, we call the corresponding transformation linear. So down here
there should
is
also
the
be something
first
from you.
coordinate of the
These are
output
construction
vector.
workers.
And there should be something here that forms my second coordinate of the output vector. So for example, it could say x1, x2, and the day you calculate it, and work that out and work that out, and we will do that in a moment. Then you get two numbers. The top number you get when you calculate that is y1, and the number you get when you calculate that is y2. And that means that what you get out of it is a vector y. How many dimensions does that vector have? 2, because it takes two numbers to describe it. And how many dimensions did the x vector have? 2, namely x1 and x2. So this x vector I've come up with here has precisely one
minus
vector.
xn over xt.
So you can now see what this means, what is written here. We have a function f, or a transformation f, that sends us from the two-dimensional space into the two-dimensional space. For the vector we use as an input vector has 2 dimensions. And the vector I get as an output vector also has 2 dimensions. Now let's try to make it concrete by inventing a specific vector x. So now I'll assign a number. Let's say the vector x is called -1/3. This means that its first coordinate is -1, and its second coordinate is 3. And that means I could draw this vector x. If it starts here, it should go 1 to the left and then 3 up. So it might look like that.
The fact that the image is vector x.
And where does it exist? That vector, it exists in a space called the vector space, and it is the vector space V when I speak generally about it. And now I can try to send that vector on a journey with that transformation mentioned here. So what does f do to x? Let's try to investigate that. What happens when f acts on the x vector? Well, what happens is you take 2 times the first coordinate plus 3 times the second coordinate. So that's what we do. And the reason it happens is because it's something I just made up and imagined. There's nothing special about this example. It's just something I invented. The only special thing about it is that it's linear. And similar means we can only multiply by constants and add together. Then someone might ask, you're not adding there, you're subtracting. And subtracting is the same as adding. If you first multiply by a negative number and then add, that is equivalent to subtracting.
I will first say it twice for the coordinate.
And the first coordinate is there, because up here, it's the first coordinate x1, and that is the second coordinate x2. So I should say 2 times x1, which means 2 times -1. And then I should say plus 3 times the second coordinate, so plus 3 times 3, because the second coordinate is 3. And if you calculate this, you get a number.
What is
I
it for?
could write that there. We get 9 minus 7.
And then I can figure this out. It gives minus x1 minus x2, which means minus minus 1. That must be plus 1.
And then minus 1,
x2,
that is minus 3.
well, that must be -2.
So we see that what we have here is a vector.
And that is my output vector y.
So what we can see is that we have come up with a slightly more advanced function machine. We're used to a function machine taking a number as input and giving the number as output. But a transformation takes a vector as input and gives a vector as output. And it turns out that this knowledge can be useful for an engineer to have an understanding of such machines. That's why we look at them, all those similar transformations that take vectors in, do something with them, and send vectors out. Question from Nikolai. There is no graph here. There is a machine that does something to a vector and creates new vectors. And you can't draw it as a graph like you can. The question was, what does a graph look like to the microphone, which couldn't hear what the question was from Nikolai. What did you say, Nikolai? Yeah, so what Nikolaj is saying now, it was what he had expected. That there were no rakes. That was quite nice.
Okay, so
What have we learned from this? If I choose an input vector x, I can generate an output vector y. So far, so good. Now we are going to discover something that is crucial for the headline. We will discover that linear transformations have a super neat property. We will discover that together now, not in this example here. So here comes the discovery. Let's try and see what happens if f acts on a very simple vector, namely the one called I. What is the vector I again? Oh yes, I is a unit vector on the x-axis. So
1.
is this unit vector, which goes 1 to the right and 0 up.
One of the weaknesses is
That's
y,
what we correctly
when
call
it's
it.
long. And this one is indeed, it's long.
Let's see where it lands.
After it has been sent off by f,
So what should we do? We need to say 2 times the first coordinate plus 3 times the second coordinate. So let's do that.
Here I have the first coordinate, and it is 1. And plus 3 times the second coordinate, but the second coordinate is 0.
Let's try to figure out what we get when we calculate the y coordinate listed down here. So the second coordinate of the output vector is minus x1 minus x2, which means minus
Background noise.
needle. And up here, I will just give 2, because it just says 2 plus nothing, so 2. And down here, it will say minus 1. And then you look at it and think, okay, that gives 2 minus 1. That was exactly what was actually here, 2. And minus 1, it was like here. The two numbers that were stacked one on top of the other, that was exactly what it gave when you inserted the unit vector I. That is somewhat important. So let's try to find the image, as it is also called. This is the image of I, and it results in the output vector 2 and negative 1.
So this
I will
is
not
an
take what it's
output
called.
2, 1.
And every time we find out what the input vector gives when it has been sent, we say that we have found its image. So f of a vector, what is that? It's the image of that vector. So what is the image of the I vector? It is the vector 2 over negative I. Now I would like to find the image of the unit vector j. And we know that the unit vector j, we can write it up here. The unit vector j is not called 1 over 0. It's called 0 over 1 because it goes purely in the y-axis direction and not at all in the x-axis direction.
If I find a picture, what do I get then?
Then I get, just like before, 2 times the first coordinate plus 3 times the second coordinate. That is 2 times 0 plus 3 and times 1. And down here I get minus x1 minus x2. So I get minus 0. If it is 0, of course, and then minus 1.
And make it come alive.
Then I get 3 over minus 1.
And this is now the output vector. So this is the image of j.
And you can see that it matches completely by standing here 3, 1. And it is not a coincidence, as I will prove in a moment, that it always holds true. Also notice another thing. If you were to write down what y prime 1 should equal, then y prime 1 equals that. And if you were to write down what y prime 2 equals, then y prime 2 equals that. These are two equations with two unknowns. So actually we can see that a linear transformation from R2 to R2, as we have written here, is two equations with two unknowns.
Okay. So it will say that y1
Is equal to 2 output plus 3 times 2.
It was just an equation.
So there is another part below, namely y2.
is equal to minus x1.
Minus x2. And so two equations with two unknowns, we've worked quite a bit with that here in class. It is said that there is a coefficient matrix that contains the coefficients.
Equation system. And where are they now located?
Well, they are right here. 2, 3, negative 1, negative 1. So our coefficient matrix looks like this. It's a collection of those coefficients, right? So it's 2, 3, minus 1, minus 1. And take note of the first column. Yes, what is that? That image is I. That column is exactly the same as that columns. So the first column in that coefficient matrix is the image of English vector y. And that one there is the image of the English vector j.
And by now using what we have learned.
It's called matrix vector multiplication. This allows me to write everything here much more briefly. This entire explanation I've come up with here can be shortened by using matrix vector multiplication. It can indeed be written like this. What does f do to the input vector x? Yes, it is written here what I have deduced, what should happen to the input vector. But it can actually be written so simply here. You just have to take that matrix, multiply it by vector x, and out comes y. And I will just show you that it is indeed true, as we have defined matrix vector multiplication.
Because what kind of matrix was it again?
You were genuine, Arb.
Serious them. 2, 3, minus 1, minus 1. And that multiplies directly by x. And x, what kind of vector was it? It was the one called x sub 1 over x sub 2.
And then
Remember the
Let's
limit
see
over
if
there.
we can go
Vector
matrix.
multiplication.
So
Blame the man.
it was something like this with the left hand, and like that with the right hand.
And then one should be able to remember how to.
pulling. So I'll take away the first row.
And dots by the first column.
So it's that 1 times that one.
Go
Yes,
for
that
it.
gives 2 times x1 plus 3 times x2. So let's just write it down. 2x1 plus 3x2. And here, when I take the second row and this column and dot it with that, then I get minus x1 minus x2.
Then you can see that what I came up with over here was written here.
That is exactly what I get here when I multiply a suitable matrix by the input vectors. How important is it? It is extremely important because what we just discovered in an example is that a linear transformation can always be written as an appropriate matrix multiplied by the input vector. And the suitable matrix is called a transformation matrix, for it is the one that maps from that vector space to the other vector space.
Knowing that one multiplies with them.
So A is called a transformation matrix, and I probably need to write that down.
On the next board, as I don't really have space here. But that matrix there is called a transformation matrix.
And I'll just move a bit to the side while a picture is being taken.
So let me tell the story again while I just point here. Okay, and now you're done writing so you can think more clearly. The headline of linear transformations, what is it? It's a kind of function machine, but it doesn't take numbers as input, it takes vectors as input. And it does not deliver numbers as output, it delivers vectors as output, so it does not have a graph. But it has some properties, and those are what we discover. Whether they are more stretched, and that's why it takes a bit longer to get used to the concept. So what is happening? Well, you have a space filled with vectors, and all the vectors you can use as input are located there, so I call it the input space, and it is named V. It's just a name, there's no understanding in the name. But you also can't understand why my name is Djembe, it's a matter of definition. F sends vectors from the input space over to the output space. The output space has been given the name W for some unknown reason. It's not certain that there are the same number of dimensions on that vector as on the other vector, but there could be. Generally, though, there aren't the same number of dimensions, and you'd need to be lucky. Here is an example of a similar deflection. Here, I have devised a function that takes x vectors as inputs and generates y vectors as output. And I came up with it in a very particularly simple way. The only thing that happens with the coordinates of the input vector to generate the output vector is that they are multiplied by constants and added together. And when that is the only thing that happens, it is called a linear transformation, which is particularly neat. Here, I have come up with something specific, so we can calculate what happens if the input vector is called that, then you get that. So that is the output vector corresponding to that input vector. That's all there is to do. Let's make an important discovery. What do you get if you let the input vector be one of the vectors we love most? Namely, the unit vector I. Then you get a vector where the coordinates match the numbers I came up with over here that were in the first column. And that's important. What do you get if you send the j vector, the second unit vector? You get 3, -1, which is exactly what was in the second column of my invented example. You write out the two equations with two unknowns, which is actually written here as a vector equation. When you write it down, you get a coefficient matrix where the first column describes where the I unit vector lands, and the second column describes where the j unit vector lands.
Growth and loans. It is super important.
Because if you want to create a linear transformation that does something specific, for example, rotates the plane, the only thing you need to know is where the I unit vector lands and where the j unit vector lands. When you have figured that out, you just take the numbers that describe it and put them into a matrix. And then you have your transformation matrix, and then you have your linear transformation. Okay, so that's an important discovery.
I haven't proven it yet, but I will soon.
So that was written on the board. What I wanted to write on the next board was that matrix, called a transformation matrix for the linear transformation.
So we can write that on the next board first.
The thing with whiteboards is that as soon as you find a marker that works really well, it becomes equally hard to erase afterward.
So that matrix I just showed you,
The dearest,
A mapping matrix.
and what's cool about it is that as soon as you have it, you can write your linear transformation like this.
What does f do to the input vector?
It does something very simple. It takes an appropriate matrix and multiplies it by the input vector. And what comes out of that?
The output vector. It has pretty much ended.
And just add the map. Everyone, it does not say ax plus b. It just says ax. If it said x plus b, then it wouldn't be a linear transformation. The only thing that was allowed to happen was multiplying the coordinates by numbers and adding them together. And this means that a linear transformation, as you will see in a moment, always sends the zero vector to the zero vector. Always. And that means it does not shift the origin. So a linear transformation can indeed be a rotation of the plane, as long as it rotates about the origin. But it must not be done like this. And moves away, making Orico move. Then it is no longer a linear transformation. So linear transformations are some quite nice transformations that do not move the origin. And in a moment, I will prove that if it is a linear transformation, it does not move the origin. Quick. If you say plus b, then you get a different transformation. It's just not a linear transformation. It's not because it's impossible. It just doesn't fit into what we are currently learning about. Are there any other questions? Okay. Are you ready to keep your focus? Because now I will try to generalize it. And it's not going to make it sound any easier.
It doesn't do that, but it hasn't become harder either. It just sounds harder without actually being so.
So therefore, you have to stay focused, trying to ignore the difficult language a bit while learning the complex language at the same time. What does it mean for a transformation to be linear? If you have to say it a bit more formally for an oral exam.
in
transformation. F, which sends us from a vector space V into another vector space W.
air, linear.
Visst, the rules apply. Okay, what is true? What is V now? Well, it is just the input space.
What was W? Output the room.
But because it is general now, it does not need the same number of dimensions.
Okay, here we are.
It could be that V is n-dimensional. So here there are n dimensions. All vectors that exist here have n dimensions. Then we are mapped by F into W.
We have M, which represents the seagull's dimensions.
The vectors that reside over here in V, they can become X. I will draw it. It's not certain that I can, because if the number of dimensions is greater than 3, then I cannot draw it. But I'll just call it X and put an underline to indicate that it can have as many dimensions as needed. However, it must be a finite number of dimensions, because what we have right now is not infinitely dimensional vectors. It is a finite number of dimensions. Vectors with finite dimensions, and over here the output vectors will land. They are called y, and I put a subscript on them. And now I'll just draw such a vector, although it's not certain that it can be drawn, because it could be 27 dimensional, so it's not guaranteed that it can be visualized. And over here are the vectors w. What I want you to imagine now, before I can tell you what it means when the lines are stated more mathematically correctly, is that I pick two vectors from my input space.
And a mathematician would write it like this.
Let vector x1 and vector x2 be picked from the set of V. That's what's stated there. So it indicates that you have gone over and grabbed two vectors from the input space V. Are you following so far? Just imagine them. They can have 27 dimensions, or 50, or 10,000. So how should I imagine such a vector? Well, if it's a 10,000 dimensional vector, then there are just 10,000 numbers in the column. Just see it as a whole bunch of numbers gathered in a column like that.
One can no longer see it as a physical object when it has so many dimensions.
So it becomes an abstraction. And then you should also imagine that I have two constants. So let's go up.
And leave.
Alpha and beta. And here I'm using short notes because I find it a
Quick
bit
stuff.
difficult
It's just
to figure out what
strange
is
to
written.
write everything down to pray. But you could also just write K1 and K2 if they prefer it, right?
It should be constant. And you write it like this if you are a mathematician.
So it's about consistently picking it in real numbers. So it could be 27 and it could be negative 39, for example, in two numbers. So what it says now is pick two vectors and pick two real numbers.
Yes, one. The following should be true. And now I'm writing it down. If I let f act on a dynamic combination of x1 and x2.
It was said with mathematics and language. What does it mean in Danish? It means take alpha and multiply it by that vector, take beta and multiply it by that vector, then add them together afterwards. Then you have made a linear combination of them. So take alpha and multiply it by the one vector.
One vector that came from over here from V.
And take a
Beta is up on the other scale, so it came from over there.
Now you have made a linear combination of two vectors.
If f is right there,
This is supposed to result in something specific. It should turn out very nice. And now it comes. It should create alpha. The image is the first vector plus beta times the image of the second vector. I don't know if you find it particularly pretty, but I think it's pretty. Because what it says here is that if you have a linear combination of two vectors, then you send it off.
what do you get then? The same linear combination.
The same alpha, the same beta as before. But now it's not a linear combination of x1 and x2 you get. It's that the images are x1 and x2.
Okay,
Look ahead,
I need
move.
to let that sink in. A transformation is linear if it
Sends linear combinations of vectors into the same linear combination of the images of those vectors. And it's simply not possible to formulate it for a successful exam unless one has practiced and tried it a few times. A function or a transformation is linear if it maps a linear combination of two vectors from the input space into the same linear combination, but of the images of the vectors. Because this is the image of x1. This is where x1 lands, and this is where x2 lands. It is the image.
X1 vector and what corresponds to the image of the x2 vector.
And that is quite a pale
Now-
quality, that one.
That is sent with something. If you are finished now. And then there may be some who say that I still understand what it means. Well, now I'll get to what it means. It means that the only thing that has happened is multiplying the coordinates of the x vector by constants and adding them together. If that is the only thing that has happened, then this is true. Still, some might think I still don't get it. So let me paint a picture for you. If the only thing happening to the input space before it becomes the output space is that the origin remains in the same place, it does not move.
And all the grid lines that were there before.
They are still parallel to each other over here in the output space. And there is an equal distance between them. That's what it looks like. So here I have said the same thing in 3 different ways, but you don't really understand it until you have seen some examples. And it starts to become clear what it actually means. And that's why it's the example that drives understanding more than the mathematician's way of saying it. Okay, so let's take another example on the next board. Then you can see that it's really true. Then you can see that it's true. Because it was only when I sat down and worked through my own example that I started to realize what it really was that I was talking about. So on the next board, let's take another example before I prove what I want to prove.
I figured it was something like this.
I'll need to move a bit here.
Okay. So here comes example 2.
Those who watch us think it's difficult. I never let it seem that way. The only thing you need to do is be able to multiply metals together.
And then you have to learn the language.
As precisely as possible, that is what mathematicians are good at. Creating a language that is completely precise. But at the same time, the more precise the language, the more impossible it is to understand. And that's why most math students start out being good and then gradually get worse and worse. What I mean by that is when a mathematician wants to write a book, they always intend to write a book that all students can understand.
So he is writing a really good math book.
So it was written in a very pedagogical and understandable way with many examples. But it's not 100% mathematically correct and precise. He has sacrificed a bit of it to make it understandable. And then he gives it to a colleague before they publish it. The colleague is also a mathematician. So he finds all the places where it isn't 100% correct and asks him to fix it. And he does fix it because he doesn't dare do otherwise, as no one wants to write something that's not completely accurate. And now the book becomes a bit more correct and a bit more useless. And then we continue until it is 100% correct and almost 100% useless. Only those who already know it understand. And that's how almost all the math books I've read are. And I came across a math book at one point that wasn't like this. And maybe you can find it if you want. It can be found online and simply downloaded in PDF. And I think it's called Calculus Made It Easy. And it was a professor who wrote a math book and stuck with the language he had devised himself. And he didn't let anyone else revise it. And it is not 100% mathematically correct and precise, but it is much easier to understand. So what I'm also trying to do is to sacrifice a little bit of accuracy in this course to gain a bit more understanding, and I hope it works. Otherwise, you can help me with feedback. But here comes an example. So let us once again come up with a similar transformation. And we'll take one that simply maps us from the two-dimensional vector space into the two-dimensional vector space, just like before. We'll take a very simple example. So here it is. F of input vector x is
Season 2, episode 1 to season 3, episode 2. 3 by 1.
plus 4x2. And what I would like to show you is that if you choose two x vectors and two constants and make their linear combination and send this off, I'd like to show you that it gives the same result as if you first sent the first vector, then the second vector, and then made the same linear combination. That's exactly what I wrote down before. And that's what I'd like to show you works in practice. So I want to show you here that f is a constant multiplying one vector plus some constant times another vector. I would like to show you that it results in this. It gives the constant times the image of one vector plus the other constant times the image of the other vector. And I would just like to show you with an example so you can see what that means. This means the following. I need to come up with an alpha and a beta so that we have some numbers to work with. So let's say alpha is 1 and beta is 2. And what else do I need to invent? I also need to come up with
An
a beta.
x1 vector and an x2 vector.
Here I've written the vector lines underneath because it's in an arbitrary number of dimensions. But here I've written the vector lines on top because I know it's two-dimensional. So I just need to come up with an x1 vector.
We can take a simple one called 1 over 2.
Then I need to come up with another x vector. And I'll just call it 2 over negative 1. And I'm just making this up. There's nothing special about the numbers. I'm not trying to calculate it beforehand to get a nice result. I'm just jumping into it and hoping I calculate it correctly. What can I do now? Well, it's a vector, it's a vector, it's a number, it's a number. So I can form a linear combination of the two vectors with the two constants. And what does that mean? It means taking the constant times that vector, taking the constant times that vector, and adding them together. Then you get a linear combination of them. Somebody just decided that's what it should be called, a linear combination. So now I form an alpha x1 vector plus a beta x1 vector and calculate it for you. What does it give? Well, alpha was 1 and x1 vector is 1 over 2 plus beta, which is 2 times the vector 2 over negative 1. And now you can see that what I'm saying is true. All that's left is to multiply and add. Now I can calculate what it results in. It gives this times that plus this times that. Then I have the first coordinate. So that's 1 plus 4. That is 5.
Then I take that times that plus.
Back then it
It
did.
gives 2. Minus 2. That's 0.
Are you following this?
That's the vector I'd like to insert here now.
For it is precisely alpha x1 plus beta x2. That is what I just calculated, and it is there now. Alpha x1 plus beta x2, that is the vector. Now I want to see where it ends up if I send it off with f. So now I just send it off with f. So what does f of alpha times the x1 vector give? Plus beta times x2 vector. What does that give? It just gives f of this vector.
Good evening.
Because that is the vector as this becomes in the end. Are you okay? And you'll soon get your break. I can see it in you. So what does that give us? Well, let's just go up and see what the number should be. You should say 2 times the first coordinate minus 3 times the second coordinate, because that's what I came up with. Is this a linear mapping? Yes, because the only thing that has happened is multiplication by constants and addition. So it is linear, as there is nothing like sine, cosine, square root, or any other complex function. Whatever it may become, it is linear. So what does that give? It gives 2 times x1. 2 times x1, but not setting 5. And then it gives minus 3 times x2, minus 3 times x2, with x2 being 0. And below it says 3 times x1, which means 3 times 5, plus 4 times x2, that is 4 times 0. And if we calculate it, it gives 10, and that's just 0. So here it says 10, and here it gives 15, and that's 0. So it gives 10 over 15. So what kind of vector is this? It's the image of this linear combination. I would like to test if it gives the same result as when I do it like that. So what I have done now is that now I want to do that. And then I want to see if it holds true when it is correct. Because then you will start to understand what it means for the equality sign to be true. So let's try to calculate that now. So now we calculate. Now we calculate this. Now we take alpha times the image of x1 vector plus beta.
Scene switches to x2.
Notice that my vector lines are now over because I am in a two-dimensional example where what I wrote here applied to all linear transformations in the whole universe. So now we can try to figure it out. What does it give? Oh, right. What was alpha? Alpha was I. Then I need to multiply it by the image of x1. See, this is the image of x1. So I need to say f of x1.
I prioritize 1 over 2.
And then I have to say plus beta, which means plus 2. And then I need to take the image of the other vector I came up with, which is 2 minus 1. And there we see what it results in. The image of that vector, it is shown here where you do it. I have to say 2 times x1 minus 3 times x2. That is how you send it off. So I have to say 2 times x1. 2 times x1 minus 3 times x2.
X times x equals 2. Just like that.
And then I have to say 3x1, that is 3x1.
Plus fire.
Times 2.
There we go.
This is how you find the image of the vector. The formula is right here.
And then I should say plus 2.
Multiply. Now I need to calculate this. So what should I say? 2 times x1, meaning 2 times 2. Minus 3 times x2, where x2 is minus 1, like that. Then I should start over here again to find the second coordinate. So I need to say 3 times x1. So 3 times 2.
Plus 4.
Times x2, which is negative 1. And let's try to calculate all of that and see what it results in. I hope it gives this.
And then I calculated the wrong place, didn't I? So we'll do it like this.
And I apologize for this chaos here, but I hope you're following along.
So I will continue calculating and just write it down again here.
2 minus 6, that is minus 4.
Minus 4 times 1 is still minus 4.
3 plus 8 is 11.
So this gives the vector negative 4 over 11. Now let's calculate this.
4 plus 3. That is 7 times 2. That is 14. And here is 6 minus 4. That's 2. And 2 times 2, that's 4. How do you add two vectors together? The first coordinate is added to the first coordinate. The second coordinate to the second coordinate. We went over this a few weeks ago. So that obviously gives 14 minus 4, which is 10, and 11 minus 4, which is 15.
Sweet, can I check if it fits?
That gives the same as that, and that is not the case. It wouldn't have mattered which two constants I came up with, nor which two input vectors I came up with. Why for F aligner? And what does it mean? This is true. So you can either calculate that first, then send it off with F, or you can send x1 off with F and x2 off with F, and then multiply by the same two constants. And it has a very specific geometric meaning, which you will discover a little later. And I think I have figured out a way to draw it in SolidWorks.
So you can show it. So you can see it with your own eyes that it is salt. But not right now. I just need to fiddle with it a bit. Maybe after the next break or the one after that.
So now I'm beginning to get an idea, purely algebraically, of what it means for something to be an aligning. It means there are some sequences you are allowed to swap.
Now we'll take a break because it's almost half past.
So let's say you have a bit of time to digest that. Let's meet at 10:40. You'll have a 12-minute break if you want to pause the recording. So after the break, we've reached board 4 here. It's completely empty, so let's fill it with some more examples. Now let's try to show some examples of how one can create it oneself. A transformation matrix that does what one might want. So let me try to invent something that is a similar transformation and create the corresponding transformation matrix. So here comes example 3. Let's say for some reason we want to zoom into a coordinate system. This could be on a computer screen, for example. But we don't want to zoom equally in both the X and Y directions. Let's say we have a coordinate system here. Before we have zoomed, where my unit vector I is located here.
And my unit vector j is right there.
And we know that the unit vector I has the coordinates 1 over 0. And the unit vector j has the coordinates 0 over 1. Now we want to zoom in. So zooming could be an example of a similar transformation, even when you're not zooming equally on both axes. So this here is my input space, and when I have zoomed, I end up at my output. So let's say that when I have zoomed, so I have kind of scaled my unit vector by a factor of 2. So now it looks like this. That is unit vector I after it has become twice as long, and therefore
The
it is.
image is the unit vector, Isai.
If I were to tell you that it has doubled in length, then what are its coordinates? It would not be 1 over 0, but 2 over 0. Now you have to go 2 out and 0 up to reach the end of the vector if you start at the origin.
And let's say that in the y-axis direction.
This was the x-axis and this was
In the
the
y-axis direction, I have scaled by a factor of 3. So it looks like this.
So this is the image of the j unit vector.
And the coordinates for that vector, the one that is swapped, are j. That would then be 3, or 0 over 3. And I need to go 0 out and 3 up to reach that place. Now I have everything I need to create a transformation matrix. The transformation matrix that does that scales the universe by a factor of 2 in the x direction and a factor of 3 in the y direction. You can see I get this kind of grid pattern here where we say we draw. But in grid lines, it looks like that. And it looked like this at the beginning. What has actually happened from here? Well, if I stretch the x-axis by a factor of 2 and stretch the y-axis by a factor of 3, an area that was here before, which was only 1 unit large, will change.
It will be sent to you, Jarl, who is located over here, which is 6 large. So Argella has been
A
scaled.
factor of 6 in this linear transformation. The small area that used to be 1 gets expanded to be 6. This is because I'm scaling by a factor of 2 in the x-axis direction and by a factor of 3 in the y-axis direction. And what we saw earlier is that if I use this as the first column in a matrix and that as the second column in a matrix, I get a transformation matrix that scales by a factor of 2 in the x-axis direction and a factor of 3 in the y-axis direction. So my transformation matrix A, for this line of transformation, it will lift
2 to 0 is the first pillar.
and 0.3 as applied. Didn't quite notice something interesting. What do you get if you calculate the determinant of the mapping point? If you calculate the determinant of this transformation matrix, you get this times this minus that times that.
Well, it's just 2 times 3, so maybe 6.
So we have now learned that the determinant means something more than what we previously understood. It is not just interesting for it to differ from 0 to no. Is it different from 0? Yes. It's also interesting to know what it is. It is 6 because the number 6 tells how much the areas have been scaled. So what does my linear transformation look like? It looks like this. F acting on input vector x.
A is equal to matrix A times X.
But that I always find it distasteful.
Can I only tell where I and j end up now?
No, I can tell where anyone ends up because I have a mapping.
So now I can come up with a completely random vector. I'm coming up with a totally arbitrary vector x now, which is called 7/8. And now I would like to know where it ends up. Where does that vector end up after this linear transformation? It's just like this. What does f of x give?
Well, that gives matrix A times X. So it gives, that makes 2003.
2, 0, 0, 3. This matrix multiplied by this vector 7, 8. And then you just need to do matrix vector multiplication. This times that plus this times that. Left hand does this, right hand does that. So that makes 14 and nothing.
And then it's like saying that time, just that time.
So that's 21 and, sorry, 0 plus 24. So it's 24. So a vector that previously had the coordinate 7/8, what are they called afterwards? If you do like this with the x-axis, a factor of 2. And at the same time, do like this with the y-axis, a factor of 3.
That aligns it so it becomes that vector there.
Can you imagine that? We have a vector that goes 7 out and 8 up. And afterwards, when it ends up over here, it goes 14 out and 24 up. Because it is scaled by a factor of 2 in the x direction and a factor of 3 in the y direction. And that process is a linear transformation. Okay, try to look at something interesting. This vector that I started with is called 7/8. What does it actually mean when it says 7/8? Yes, this 7 means that I stretch the I unit vector by a factor of 7. And the number 8 means that I stretch the j unit vector by a factor of 8. And then I add the two vectors together. Are you with me on that? That's what this coordinate column means. Take 7 unit vector I plus 8 unit vector j. Are you following?
But just try to see what happens next. What will f be? From the x vector? Well, it simply can't do that. We know that.
But this also gives. And now something important is coming, so please listen carefully here. 7/8 means taking 7 unit vectors, I plus 8 unit vectors j. So 7 units plus 8 units. Now something super elegant is coming. Where does that vector land? It still lands 7 units ahead plus 8 units ahead. But it's not supposed to be in I, and it's not supposed to be in j. It should be the images of I and j. This also gives 7 times the image of where I lands, plus 8 times the image of where j lands. So that gives 7 times what? Where does I land? We know that. It lands at 2, 0 because it had been stretched by a factor of 2. Okay, plus 8 times the image of where j lands. And where did j land? It landed in 0, 3.
So you get 14 plus nothing. That is 14.
And you get 0.
Plus 24, that is 24.
And now you have actually seen why matrix vector multiplication is defined that way at all.
That's because this is true again.
So slowly and calmly, a picture of the connection begins to emerge. Okay. Now here comes something that I think is really cool, right? The determinant of this mapping matrix. What did it give? 6. Why do I think that's cool? Partly because it tells how much the areas are scaled. Also because it tells me that I didn't lose dimensions.
Ooh, what is it that he mentions, Mr. Dimensioner?
Well, imagine that you make a transformation from here to
Set the
there.
task here, and I'll do that right after on the next board.
You do nothing to unit vector y, but you rotate unit vector j down on top of it. Now we get a transformation that takes the plane and projects it onto a line.
So we go from a 2-dimensional vector space to a 1-dimensional vector space, if I do that. Is it a linear transformation? Yes. Why? Well, because it maps the 0 vector to the 0 vector.
And all the grid lines that were there before,
What should be parallel to each other are still parallel afterwards. So it is a similar transformation, but I lose 1 dimension. Then the determinant becomes 0.
So when the determinant becomes 0, you lose dimensions.
Okay. And it's pretty cool. Because we reach a point called the structure theorem, which tells how many dimensions are lost when you have a similar transformation. And I have a small personal philosophy that we humans live in a reality that is just a shadow of a reality with more dimensions. Apparently, there's some kind of transformation through which I perceive the world, from a reality with multiple dimensions, where we are a shadow image of that. So the determinant is 0 in that transformation. We have lost some dimensions. We cannot recognize or experience them. This is what string physicists believe. They think there are 9 spatial dimensions, but we can only perceive 3. So we create a shadow of a shadow of a shadow of a shadow. And in the end, there are only 3 dimensions down here that we can perceive. One can use this math to philosophize about such crazy ideas, which are, of course, incredibly difficult to prove, because how could I ever measure something beyond what can be measured with physics? But it's fun to think about, at least. Let's now try to create a linear transformation where the determinant is 0. So that will be board 5. And example 4. So now I imagine that we have our input space here. It is 2-dimensional.
and here is the unit vector I. And here is unit vector J.
And here is some random vector I just come up with. It is called the X vector. Could I now create a transformation that finds the shadow cast by vector X? If I position myself and shine a light from up here, I shine a light such that it beams directly down onto the x-axis, which is right there.
And then vector X casts a shadow.
And then I'm lying there. So I want to see if I can create a linear transformation that always just gives me the shadow of a vector. Do you now understand what I mean by suggesting that maybe we live in a shadow world of multiple dimensions? Or perhaps we are the result of 4-dimensional vectors casting a 3-dimensional shadow. And one could imagine that this vector X has 2 coordinates. And maybe I should call this one the X1 axis, and this one the X2 axis. So this is just called X1 over X2. If I want to find the shadow, and this down here is the shadow, then I've been a little bit,
Not just because I drew
from,
the
for example,
picture.
the grenade system.
It was just so you could imagine the shadow.
So this is the shadow of the X vector. What coordinates does it get? Yes, the shadow, which means the image of the X vector. It still has the same X coordinate, but its Y coordinate is 0. Can you see that? Because it lies right on the X axis. So it must be called X1 over 0. How do I figure out what my transformation matrix should look like? Well, I just need to think about where the 2 basis unit vectors end up in this transformation. So if I ask you, what is the projection of I? It is I, right? So the image is I is equal to I itself. Isn't that right? Have you given weight to these coordinates 1 over 0? So I could ask, what is the shadow? It is the J vector. If I shine from above down onto the J vector, where does it land? So it just lands as a point, directly down at the J vector. Isn't that right? So the image is J.
Vector, we are at 0 vector.
And a 0 vector is a very special vector that has a 0 as both its first and second coordinate if it's a 2-dimensional 0 vector. If it's a 10-dimensional 0 vector, then there are 10 zeros down here.
Are you ready to achieve this or what? Well, now I can form my transformation matrix because we have learned that what should be in the first column of a transformation matrix is the image A, and that is 1, 0. And what should be in the second column is 0, 0, and that is the image of the other. And here I have it. Here I now have a linear mapping called f of x vector is equal to that matrix A times the x vector. And what does it do for us? It finds the projection of a vector down in the x direction.
And what is the determinant of that?
What is the determinant of my transformation matrix?
The times that minus the times that is 0, minus 0, that is 0. So the determinant is 0. What does that mean? An area that used to be consistent
As now becomes 0.
because it has simply collapsed the entire y-axis down onto the x-axis. So I have moved from 2 dimensions into 1 dimension. Because I know that all the output vectors have their other coordinate at 0, I can just think of it as a 1-dimensional vector coming out. Yes, the question is asked whether one can find out how many dimensions are lost, and that will come later in the necessity for structure setting. So the question somewhat belongs to the future. I hope you are starting to get a picture of what that means.
Indicates having a similar transformation.
A linear transformation is something that acts on a space of vectors. So you get a new space of vectors, but they do not need to have the same number of dimensions. You can lose dimensions along the way.
And the question.
Try listening to Søren. I believe you can. We can try to take an example. Let's see if we can add another dimension to what we started with.
Now let's try it.
Yes, we can handle that here. Example number 5.
The question was asked, can you also have more dimensions? Imagine that I have a similar mapping that takes me from the 2-dimensional vector space into the 3-dimensional vector space. You write it like this. What would it look like? Well, my input vector is in the space. How many coordinates should it have? 2. So here is an x input vector. It's called x sub 1 over x sub 2. And over here in the output space, the output vectors y need to have 3 dimensions, meaning there must be y1, y2, and y3. Now I will try to invent such a linear transformation. And what were the requirements for a linear transformation? It must send the 0 vector to the 0 vector. And the grid lines must remain parallel and equidistant. That means equal distances between all of them. So here comes an example of such a mapping. I might need to come up with a way to generate y1, a way to generate y2, and a way to generate y3. So it could be 2 times x1 minus x2, and then I have a y1 coordinate. Remember, the only things I can do are multiply by metal and add together. And here I might say minus x1 plus x2, and then I get y2. Then I just need to make one more. So here I can say 3, 2, 1.
Plus 4 times 2.
And out comes a vector of y, which has 3 dimensions. So this is an example of a linear mapping that takes us from the 2-dimensional space into the 3-dimensional space. Thus, we gain an extra dimension. And the only thing that has happened is linear operations. I've multiplied by constants and added together. So does it hold that if I input a 0 vector, I get a 0 vector out? You can try and see. If now I say, what does f of the 0 vector give? What coordinates does the 0 vector have? Well, the 0 vector is a very special x vector because it must lie over here in the input space. It has 0, 0 because it was 2-dimensional. So x1 is 0, x2 is 0. What is 2 times 0 minus 0? 0. What is negative 0 plus 0? 0. What is 3 times 0 plus 4 times 0? 0. So the output vector becomes 0, 0, 0, a 3-dimensional 0 vector corresponding to the 2-dimensional input 0 vector. So the origin does not move, but we get an extra dimension.
See.
Yes, now there is the challenge that the determinant can only be calculated from square matrices. Quadratic matrices. So that will come a little later, the whole overall overview. Are there any other questions now? Okay, I've used the word vector space a few times. So let me now provide a more precise explanation of what a vector space is. There is also something called a subspace in a vector space, which we also need to know about.
So that will be on the next board.
Now we are at section 6. So the title is vector space. So it's a question that naturally comes to mind immediately when you hear the headline, what is a vector? So we will try to answer what is a vector. And the first explanation that might pop into one's head isn't quite right. When I first heard it, I thought, what is a vector? Isn't it just a space filled with vectors? End of story. It is actually close to being correct, but it's not completely accurate. There are certain criteria that must be met for us to call it a vector space. It is true that a vector space is a space filled with vectors, but there's a bit more to it than that. So a vector space, and here we have the opportunity to write a bit of text. A vector space,
Yes. A collection of a big
called vector. The eavesdropper. By ensuring
See you. Bye.
So let's say that that would be such a vector, so I can say something about it. That would be such a vector, so I can say something about it.
Be such a space.
What can I say if V is a vector space? I can say some things that perhaps you hadn't thought of before. But if you pick two vectors from that space and add them together, you should get a vector that is also in that space. It must not be the case that if you have a collection of vectors, you take two of them and add them together, you get a new vector that is not inside this
And
space.
difficult to end in one place. Do you get what I mean?
For example, if I had a vector pointing that way, another vector pointing that way, and I add them together, I get one that points that way. It must not be the case that this vector, which was the sum of the two others, does not exist within the space. If so, then it is not a vector space. That's called a stability requirement. No matter which two vectors you take from there and find their sum, it must also be a vector that lies within. Otherwise, it would not be a vector in the space.
So we'll set one up.
Vector and x sub 2. Vector both lie within the vector space V. So their sum must also lie within it, which means it can be a vector space.
That's how it should be.
Egebæk takes xz, adds together with vector x2, also lying in V. That's how you write it. That is one stability requirement. The other stability requirement is that if you take a vector and multiply it by a constant, meaning you scale it, then the new vector must also be included. It must not be missing. I will try to give an example where you can see what I mean.
Alpha is some real constant.
R, B, C, D, E, X. The X vector is inside the vector space.
Then alpha times the X vector must also lie within the growth space.
And the two conditions can be combined into one large one.
So you could basically say that any similar linear combination of two vectors from the space should result in a vector that also lies within the space. Then you have some constant times a vector coming in from V. Now it's another constant times a different vector that's also coming in from V.
This gives a new vector that must also belong to V.
These are demands.
Could I then give an example of something that you would think is a vector space, but isn't? Imagine that you have the entire plane in a coordinate system here. Are there vectors in there? Yes. There are two-dimensional vectors living in that vector space. How many are there? Infinitely many.
Red picks 2 random ones.
And add them together.
Bang. Is it in there too? Yes.
So the whole plane is a vector and it is dimension 2. But now try to imagine that you only look at this. For that is the x-axis and that is the y-axis. But you do not allow x to be negative. Are there vectors in here? Yes, there are. Are there infinitely many vectors in here? Yes, there are as well. Is there a zero vector in here? Yes, there is. But is this a vector space? No, it's not. Why not? Well, because if you take a vector here and a vector here, then it might be that if you just add them together, then it might be that if you just add them together, then it might be that if you just add them together, then you get a vector that is still inside. But what if you had taken that vector and multiplied it by -1, and took that vector and multiplied it by -1, then you would get that vector. And that and their sum will lie there, and that vector does not lie in the vector space, because I was only looking at that over there. Okay, do you follow what I mean? So there are certain requirements for something to be called a vector space. Every linear combination of vectors within the space must result in a vector that still lies within the space. Otherwise, it is not a vector space. A vector space is said to be closed under certain operations. You should not fall out of the space if you add two vectors together, nor should you fall out of the space if you multiply a vector by a number. There are about 7 or 8 rules that need to be followed, and they're not something people generally remember. But I can mention a couple of them now, and I'll address Benjamin's question afterward. A couple of things that must be followed to call it a vector space, for example, are that the order of addition must be commutative. All mathematical objects that behave like that can be allowed to be in a vector space. If they behave like that, then it can be a vector space. If they do not behave like that, then it cannot be a vector space. The sequence is what makes it matter.
And if you take a
multiplying the number 0 by a vector within the vector space should yield the 0 vector. And there must also exist a neutral element. So if you take a number and multiply it by a vector from within, you should get the vector itself. And there are about 7 to 8 rules, which I don't need to know. And I don't need them for an exam. But for something to be a stable vector space, certain rules must be followed. So you can operate with the vectors inside. That's what we call a vector space. So what is a vector space? It is a mathematical abstraction. I think of it as a bag full of vectors, and there are infinitely many in there, and the 0 vector is there too. And no matter what linear combination I make of vectors in it, I will get a vector that is also definitely inside the bag. That's a vector. A vector space can have different numbers of dimensions. It could be the 3-dimensional vector space R3 or the 2-dimensional vector space R2.
And that brings us to the next headline called subspaces.
You can actually have a subspace within a vector space. And then I'll stop talking about it because it sounds so fancy, right? But board 7, the heading is now subroom. What is an underhand? It is a subspace of a vector space. That is the first thing you can say about it, a subspace.
Is itself a vector space?
And maybe I should write a subroom U.
Yes, set it. A vector.
But it only has the property of being a subspace that it is a subset.
Of another vector space.
Then it can be somewhat less important. For example, as an example, R2, which is a two-dimensional vector space. We just saw that earlier. It is the space that contains all two-dimensional vectors. It is actually a subspace of R3. How can we know that? Well, firstly, it is a vector space itself. That is the first requirement. And secondly, it is a subset. That is the second requirement. Then it is a subspace. There are two requirements for a subspace. It must itself be a vector space, and there must exist another space in which it is a subspace. You can see that R2 is a subset of R3. It can be drawn quite easily if you have R3 here, with the x-axis, y-axis, and z-axis. So all of this is a vector space.
That's V.
But we can see that a subset of V is this entire plane down here, this entire xy plane. It is only a subset of V, but it is also a vector.
Which meets all the same stability requirements.
Exactly, yes.
So now you know what I mean when I say a vector.
And now I can't quite remember how long it's been since we took a break, because I've been thinking about vector spaces. But are you at the point where you need a break, or should we take one more step? We are moving forward a step.
Okay.
Does anyone have any questions about vector spaces or subspaces? Okay. I think I will take things in a slightly different order than I initially decided when I was practicing, because it might get a bit too abstract if I go with what I initially planned. That's why I will take something I don't find quite as abstract, and it's called basis change. That's the topic now, and it's pretty cool, because in reality, one could say, if you're a bit esoteric, that the base change is the mathematics that explains what it means to be an empathetic person. Because there are many different people, each seeing the world through their own set of lenses. And it's not that one set is more or less correct than the other set, it's just the other set of glasses. And exactly the same story applies when it comes to vectors. If I have a vector which has a certain length and points in a certain direction, it can have a set of coordinates that look completely different to Rune than to me. And to understand it
And live freely.
So this is about being empathetic and understanding that other people see the world differently. And now we will see how to switch from one viewpoint to another. This operation is called a basis change. And it seems very mathematically nerdy. And one might wonder what to use it for. But it really has some cool applications. Certain problems in physics are much easier to solve if you just change perspective first and see it with different glasses. Exactly what I mean by all this should become clearer now. So the heading is basis. Shift. And the easiest way to understand the basis change is definitely with an example, I think. I've worked through an example where I'll use the numbers from the one I came up with, so I don't get mixed up with something where the drawing becomes terrible. So in this example, the story begins with a vector A, which has the coordinates 3/1. And already I have to tell who is looking.
Who is it that says vector A has coordinates 3/1?
I can explain that by writing an E here. And it's usually left out because this might be the first time you're hearing about it. So you haven't needed it before. But what does this E mean? It means that here is a vector A and its coordinate key with respect to a specific basis, which has been named
E. So what is E? It's a coordinate basis. So we write this E. It is a coordinate basis map in just basic. And we usually call this, which I am writing up now, the standard choice of coordinates, or the standard unit basis. It looks like this. Since it is a two-dimensional vector, it's just two vectors that are of unit length and perpendicular to each other, and they are called I and J. That is called the standard basis for the two-dimensional space. Those are the two unit vectors you all know. That is a unit vector in the direction of the x-axis, and that is a unit vector in the direction of the y-axis. Okay, as soon as I have written it. Yes, so this makes sense. You wrote this in high school without pointing it out, because that's all you ever did there. But now we need to say what we mean. We mean 3 units of that vector plus 1 unit of that vector. That's what we mean when we write something like this. 2 coordinates stacked vertically are called a coordinate column, and they always refer to a basis, because without that, it's meaningless. You have no idea what it means. So I'll call that the old basis, the good old one we almost always use, I and J. I'll create a new one, so you'll hear me using the terms new basis, old basis. So who is the old one? It's the good old I and J. And these 2 vectors, they are especially nice, beautiful, and elegant, because they are of unit length and perpendicular to each other. So this, again, means 3 units of vector I.
Plus a times the unit vector J.
And I will just draw that vector for you so you can follow everything in a drawing while it starts to rain. So here we have a coordinate system. And my weight is decreasing. It goes 3 out, 1 up. So 3 units in the unit vector. It's maybe 1, 2, 3, and then 1 goes up. So it looks roughly like this. And just notice that this is my vector A, that arrow, and it continues to look like that. Because we humans believe that reality does not change depending on who is looking at it. But it can just be described in another way. So it's the same vector I've been describing, but I'm putting on new glasses. So that is what I mean by understanding the world from another person's perspective. At least we assume there is a reality out there that is independent of who is observing. This also doesn't seem to be the difficult part in kinematic mechanics, but we sort of assume this in neutron mechanics anyway. So this vector here, I call it A vector, and I don't even bother writing E, because right now I'm only thinking about the arrow. That arrow, it's the A vector.
And when I write AI, I mean the coordinate search that describes.
I write that vector with respect to that basis.
Now
And
I
then
will write
preferably
up
find
a
the
new script
basis. And I
done
hadn't done that,
completely in wildness
whether it gave a
without
P
checking
number,
what happens.
and it didn't, but at least it gave something I can calculate for you again. It resulted in some fractions, but that's okay. So I just randomly invented 2 new vectors and let them be a new basis. And the new basis I'm now inventing is this one.
We write it here.
The new basis that I am now creating, I give it a
That
name.
was some B.
Some kind of innovation. That's for the basis. You can also think of it as B for new classes. It's the same vector C with new classes. How many vectors should be in this new basis, which are linearly independent of each other? 2. Why? Because it's a 2-dimensional vector. And exactly 2 linearly independent vectors are needed to span the 2-dimensional vector space. And I must have 2. I call one of them B1, and the other one I call B2. And now you need to pay close attention, because something important is coming up. I have invented a B1 and a B2, but they cannot be parallel, because then they would not be linearly independent. If they were parallel, they wouldn't span the plane at all. They would only span the common line they both define.
So I have invented a B1 that looks like this.
And it has the coordinates -1.
Wow.
Right now, there could be someone sharp in the class asking, Jim, which basis are you referring to when you create B? Well, you can't really be in doubt about it, actually, if you just think about it. It has to be in relation to the standard basis, because if it were in relation to its own basis, it would have said 1, 0. What does the coordinate column mean again? The coordinate column means
so many of the first basis vector plus so many of the second basis vector. So the 2 and the -1 have to refer to I and j. So I mean 2 times I minus 1 times j. Why can't it refer to these two here? Yes, because if the b1 vector referred to these, then it would mean 2b1 minus 1 b2 vector. That doesn't make sense. I can't say that the b1 vector equals 2b1 vector minus 1 b2 vector, but I can indeed say that the b1 vector is equal to 1 b1 vector plus 0 b2 vector. So if I had written 1, 0, then I would know that I was referring to that. When I define the first basis vector, when it says 2 minus 1, it can only mean that I am referring to this one up here. And that's why I don't bother writing an e here, but I do mean an e here. That basis vector refers to the original I and g. Yes, that's what it ends up being. There's a question about whether it's a new scaling. Yes, it is. It's a new way to describe vector A with some new vectors called b1 and b2. Then I introduce vector b2. And the vector b2 I came up with naming as 4/2. And again, what do I mean by 4/2? I mean 4 I vectors plus 2 j vectors. I do not mean 4 b1 vectors plus 2 b2 vectors. That is not how I define b2. So it also includes b1. So therefore, I refer to the 2 vectors as I and j. Then you
The
combine
beginning of
them
asking, well, Jim, those 2 vectors you came up with, you can't possibly ask them.
as a new basis. Well, try calculating the determinant, that times that minus that times that. It results in 4 minus negative, 4 equals 8. So is the determinant 0? No, it was 8. Is it linearly independent then? Yes, it is. Does it span the entire plane? Yes, it does. Can it then be used as a new basis? Yes, it can.
Are you with me so far?
Let's go then. Oh,
Try drawing the 2 vectors down here on the same diagram. The first vector went 2 out and 1 down, so it's approximately here. That is the b1 basis vector. And the second vector went 4 out and 2 up. 1, 2, 3, 4, and then 2 up. Oh, I don't have space to write a there. It looks like this.
So now I can write that this is b2
vector, and here it is. Wake up. Did you catch that?
Okay, so the question I'm now asking myself, and we need to be clear on this as you hear me, is there a way, a number I can use to scale the b1 vector with, and a number I can scale the b2 vector with, so that after I've done that, I can add them together and get vector A?
Let me just draw that. I'll draw a line parallel to vector b2.
And I draw a line parallel to vector b1. Okay, are you all with me that the vector that is now here, this little cute vector there, is combined with this slightly larger yet sweet vector?
We are scaling the vector, and a parallelogram is drawn.
Are you with me on that? Are you also with me that this little cute vector here must be a scaled version of b1? Where are those pairs? So if I scale b1 with alpha, where alpha is a number, then I get that small cute vector. And if I scale b2 with a number, then I get this slightly larger, but still sweet vector beta b2. Are you following that?
So you can see in my drawing that the alpha b1 vector
Plus beta b2 vector, that gives vector A. All right, let's write it down. Vector A equal to alpha times b1 vector plus beta times b2 vector.
Hey, what does that mean?
To understand that, let's go up here and look again. What did it mean to write vector A in e-coordinates as 3/1? What did that signify again?
Based.
It meant a unit vector of the dive. I plus j times the unit vector. Are you with me on that? So what are the coordinates of vector A if you're wearing e-glasses? 3, 1. What are the coordinates of vector A when using b-glasses?
It's alpha beta because the two numbers here indicate how much of each ingredient I need. Just like the two numbers tell me how much I need of this ingredient and that ingredient, the two numbers tell me how much I need in the direction of vector B1 and how much in the direction of vector B2. So if I can find alpha and beta, what have I found then? Vector A in B coordinates. That's the main point. So it really needs to sink in before we move on. So I am writing this here. If we can find
Alpha and beta. What have we found? Vector A and B coordinates.
now we have found the column for vector A, but in B coordinates. So we have found
Vector A in B coordinates.
and it looks like this.
It's out.
One coordinate is alpha, the other coordinate is beta. I'll say it again, because it's really important that we understand this before moving on, as it's something we've practiced in class. This is the only difficult part of changing bases, just grasping this concept. So the story is, you have a bang vector. It does not change. It looks like this. It's the same thing we are looking at all the time.
Here's the giraffe. Want to come look at the
But
giraffe?
we are looking at it with two different sets of eyes. We start by looking at the giraffe with A eyes and E eyes mean in terms of the good old usual basis with I and J. And with respect to the two basis vectors, it has the coordinate column 3, 1. What does that mean? Go 3 times along this vector, plus go along this vector once. When you've done that, you'll have vector A. And that also works. Take 3 times the I vector plus 1 time the J vector, and you have vector A. So slowly good. But now, I've invented a new basis in which I want to describe vector A. I would like to find the coordinate column for vector A, but in basis B. So that's why I draw B1 and B2. That's nice. This corresponds to creating a whole new coordinate system. It's 1x in the x direction, 2x in the x direction, 3x in the x direction. The x direction is here now. This is a new y direction, and it's not even perpendicular. So it's 1y, 2y, 3y. And now what I'm asking is, how much should I have in this direction and how much in that direction to express the vector as a sum of the two? And the answer to that is, you just need to find out how much you should scale this vector. If it gives 1/4, it means you need to make B1 4 times shorter. So you only take 1/4 of the component B1. And let's say you have to take 5/8 a bit overnight.
Everything looks right. I can remember it completely.
Then you need to take about 5/8 and multiply by B2. Then you get it right. And now I will show you how to find the two numbers. And what are they? They are the two coordinates. To what? To a column vector, but with respect to a new one. Versus, I think this is a good point to take a break before we continue. So let's take a 10-minute break, and then we'll proceed. So we just took our break, and the story continues. We were in the process of trying to find alpha and beta, which are the coordinates of that vector. And someone might say, you already know the coordinates, 3/1. Yes, I do, but that's with respect to the usual basis. Now I want to find the coordinates with respect to my new basis B. And that really means I need to know how much of this vector to take, plus how much of that vector to take. And the two numbers, alpha and beta, tell us that. They are the coordinates of vector A, seen with B lenses. So let's see if we can find it. And we simply do that by setting up alpha times the B1 vector plus beta times B2 vector. What does that give? Well, alpha is just a constant I'm looking for. So I just call it alpha. But the B1 vector is called 2/-1. So I can write that in place of it. And in the same way, I can write beta times the vector scaled 4/2.
Sunday? Yeah.
And unfortunately,
G
is the vector A, which had the coordinates 3/1 in the standard basis. So it must be 3/1.
Now we can see that this results in two equations with two unknowns, because 2 times alpha plus 4 times beta must equal 3. And minus alpha plus 2 beta must give 1. And that is a similar system of equations. Two equations with two unknowns. So the two equations with two unknowns, we can just write them down. We'll do that over here. And here is equation 1. It will say 2 times alpha.
Plus 4 betas.
Should I give 3? That was one of the equations with two unknowns, and the other minus alpha. Plus 2 beta.
Mistress in one.
And there we have learned that as soon as one has a similar system of equations, one
Name
can...
its coefficient matrix.
So what will the coefficient matrix be? It will be the matrix that results from just looking at the coefficients 2, 4, minus 1, 2, 2, 4, minus 1, 2. And that means I can write those two equations with two unknowns all at once as a matrix division, right? Because it can be written like this. Matrix A multiplied. The vector that contains the coordinates alpha over beta. And what kind of vector is that? It is vector A, but expressed in B coordinates. Do you understand what I mean? See these two equations with two variables? How could I find them? I can take this matrix and then multiply it with the vector called alpha over beta. Let me just show you. I should probably show it. Look, if I write it like this, 2, 4, minus 1, 2. That's my matrix here. If I multiply it with this vector called alpha over beta, what do I get then? That times that plus that times that. It's 2 alpha plus 4 beta. That's what was written here. Can you see it? And if I take that row and that column, I get this times this plus this times this. So it's minus alpha plus 2 beta. And what comes out of it should be 3.1. So just take a look at what's written in this equation here. What is written here is matrix A. What is written there? That is my vector A, but in B coordinates, right? That was our conclusion. If I could find all the additional B's, then I would have found vector A in B coordinates. And what is written here? It is vector A and the usual basis, the good old basis with I and J. So what I can write down is that matrix A times A in B coordinates will give me A in E coordinates. I need to bring that up. This is important, what is written here. And that tells me how I live. And the new B coordinates in the new B basis sets it freely. And it is easy. You just have to multiply by matrix A. And you have it available, that matrix A. Where from? Well, you just take those two numbers and use them as your first column, and those two numbers and use them as your second column. As soon as you know your basis, then you know a matrix that can switch from one basis to another. And that's called a basis change matrix, that one. So this A here is usually called M, because M is typically used for a basis change matrix. I don't know why, but I've sometimes come up with that. And then you write, as you can see, it shifts from B coordinates to E coordinates. So you write a B here and an E here with two lines underneath to indicate that it's a matrix. Because then, if you write the equation that's up here again, just with that one instead of that name, it states that the basis change matrix, which shifts from B to E coordinates, if you multiply it by vector A in B coordinates, so you get vector A and the good old coordinates. And notice that the notation is cleverly designed so that if there's a B here, there must also be a B there. So the B's are right next to each other.
So again, what is this?
It's a change of basis matrix that switches from B coordinates to E coordinates. And you have to read it from right to left, which is good news for those who have learned Hebrew, I think. Bad news for the rest of us. But this should be read from right to left. This is not what I want at all. I already know that vector. I know A in E coordinates. What was it? 3? 1? So that wasn't what I was looking for at all. What I was looking for was that in B coordinates. Well, then we just use what we learned last time. We use the inverse matrix. We multiply this equation by the inverse of that one. So this matrix, which is called our inverse, it is a basis change, which goes from A coordinates to B coordinates. So you write A here and B there. And if you use that, you can set this up. Are you using M, which goes from E to B coordinates? Now you can multiply by vector A in E coordinates, which is the one we know. And what do you get then? The one you want to find, which is vector A in B coordinates. So now we can try to do it simply. Now we try to find, if I have the inverse of A, then I have a basis with the transition matrix from the old coordinates to the new perspective. It is B series. So in reality, I need to take that matrix written here and find its inverse. And fortunately, we have learned how to do that. So let's try to see if we can find it. We'll do it right up here. How was it again? Yes, you had to say that it's the reciprocal of the determinant multiplied by the adjugate of matrix A. We learned that. I remembered it last time. So we take the reciprocal of the determinant. That means that 1 divides by the determinant. What is the determinant for this matrix? It is that times that minus that times that. It is 4 minus minus 4. That is 8. So there should be an 8 in it. And it happens when multiplying by the adjugate of this one. And maybe you remember how it was found? You swap the diagonal elements. It's pleasantly easy because you can see that 2 is swapped with 2. And then you change the signs of the elements outside the diagonal. So it will be 2, 2 here and there. But here it will be negative 4 plus 1. So I'll just write it here. I think there's enough space for it. So 2, 2 on the diagonal and minus 4 plus 1. And now I can take my number, 1/8, and multiply it into all the elements within my matrix. Then I get the inverse, and thereby find a basis transformation matrix from old to new coordinates. So let's just find and write it down. What does the M basis change matrix from E coordinates to B coordinates give? Well, it is 1/8 times 2, which is 1/4. 1/8 times negative 4 is negative 4/8, which is the same as negative 1/2. 1/8 times 1, well, that's just 1/8. And when 1/8 times 2, well, that is 1/4. Now there's a fence. This matrix is interesting because when you multiply by it, you can suddenly see what coordinates the same vector has when viewed with new perspectives. Brilliant. Now you can use linear algebra to change perspectives. Let's try that. I hope I can fit it down here so I don't have to erase a whole lot, which I'd like to point at. So let's try to see if I can find vector A in B coordinates. By taking that matrix, I use the formula in the box here. A in B coordinates, that's the matrix here, times A in E coordinates. So I need to write 1/4 minus 1/2, 1/8, and 1/4. And this happens multiplied by vector A in E coordinates, which is called 3/1. That was the original vector I came up with. Thanks for today. We say this times this plus this times this. And that's how you
Matrix
make a vector.
multiplication involves pulling the facts with columns.
So that gives 3/4 minus 1/2. Let's write that down. 3/4.
Like this. But this one,
Equivalent
is-
to 2/4. So it says 3/4 minus 2/4. That makes 1/4. Did you get that? So it should say 1/4 here. So what did I do? That times that plus that times that, it makes 1/4. So I take that times that plus that times that. It's 3/8 plus a quarter. And what does 3/8 plus a quarter equal? Well, it's 3/8 plus 2/8. That makes 5/8.
And here is the answer. Who is that? I'll take care of that. Look through which lenses? B lenses, the new basis. And we think it looks right, that it gives a quarter and 5/8. Yes, take a look at my drawing here. What does a quarter mean? It means you take a quarter of that vector. What does 5/8 mean? It means you take 5/8 of that vector, and then you add them together. Look here. That vector times a quarter should become 4 times shorter. It fits quite well, even if the drawing isn't perfectly exact, right? But the little one here is 4 times shorter than the long one. And then I need to take 5/8, but 5/8 is a number that's slightly larger than 1/2, because 1/2 is 4/8, and it fits well. As you can see that this red vector is a bit over half of that vector. And when I add the little cute vector to that red vector, I get vector A. And I have now described vector A in a new basis.
And that was the story.
And this is the kind of story you would typically tell at the oral exam to show that you understand base conversion. But I will start with an example. Do you have any questions, Christian?
This one over here, well, that time there plus that time there.
That was because you had to say 1 over the determinant of the matrix, and the determinant was 8. So an 8 needs to be multiplied onto this matrix by multiplying it into all the elements within your matrix. This is the adjoint version of matrix A, and matrix A was here. So I swapped the diagonal elements and changed the sign of the elements outside the diagonal, and then I get the one shown there. What I imagine we should do now is practice it. That means we need to go out and try to tell each other about basis transformations, and you should come up with your own example. So you come up with a vector A yourselves. Expressed in the usual basis, you'll come up with a new basis on your own. Then you have to determine what the coordinates of the original vector are in the new basis. I'll walk around and help you. So this is probably where we'll stop for today, as it will likely take some time. But I can assure you that's the plan. So let's just stop the recording. Stop it completely for today.